Okay. You all doing okay this Monday afternoon? Yeah. So we finished up 12:05. There's a mini exam 4 that was due today at 1 o'clock. So I know some of you submitted that. I'll get the next one out to you hopefully today or tomorrow. And that'll be our 5th one. And then I've got a ton of grading to do. So hopefully get all caught up this week. Any questions before we begin into chapter 12, section 6? No? We're ready to get into this? All right, so last time 12.5 was about triple integrals in Cartesian coordinates. And so what we learned was that when you have a triple integral, you're not able to visualize the function, but you can visualize the region of integration as being 3-dimensional, like a 3-dimensional solid. And then from there, we can define the triple integral. And then within that, we said that there's like the most basic idea, which is your x, y, and z are all between constants, which gave us this little box, or this, yeah, like a little box. And then we said, well, you could also have like almost like a type 1 region where your shadow on the ground is x is between 2 constants, y is between 2 functions of x. And then we've talked about all the different projections you could have on the different planes. And now what we're gonna do is shift gears into a different coordinate system. Just like in 2-dimensional space, we had Cartesian and polar. In 3-dimensional space, we actually have 3 different coordinate systems that we like to work in. Cartesian, which we've done, and then we have cylindrical, and then we have spherical. So today we're going to do both cylindrical and spherical. Right, so let's take a look at cylindrical first. And so the way cylindrical works is that you're going to look at 3-dimensional space, but instead of having our standard x, y, z Cartesian, right, instead of having this, what we're going to do is we are going to replace x with r cosine theta, replace y with r sine theta. Does that look familiar? Yeah, that's polar, right? So that's basically the same conversion we did in 2-dimensional space. That's still going to stay the same. We still have the relationship that x squared plus y squared equals r squared. And then the question then becomes, what do we do with z, all right? So with z, what we're going to do is we're going to leave z alone. So our new ordered triple is the x is replaced with r cosine theta, the y is replaced with r sine theta, and our z is just going to be z. So if you ever wanted to convert from Cartesian over to cylindrical, the only thing that changes is the x and y, and the z just remains the same. So what does this look like visually? Well, visually here you can see this is us looking from the top down. This is the xy plane. Z is coming out at us. And we had already seen that if you wanted to pick a point in 2-dimensional space on the xy plane, you could also just change your angle and change your radius, and that would take you to some point in 2-dimensional space. What we're going to now imagine is that that point is in 3-dimensional space, so that there is also a z component to that point. So that point might go up a little bit or down, okay? But it lives, that point, that black point lives on some cylinder, you see? And as I adjust theta, I'm just going to swing around that cylinder. If I adjust r, then I'm just going to make the cylinder either smaller or wider. And then z is just going to move me up and down. Okay, so there's really nothing new here because we've already done polar. It's just, you know, that the space that we live in now, this system is called cylindrical. One interesting question would be if we know now that our variables here are r, theta, and z instead of x, y, z, then what would this look like? Just think about this mentally. What would it look like if I had theta and I told you it was stuck between 2 constants, alpha and beta, let's say. Let's say the radius is stuck between 2 constants, let's call it r and s. And what if I tell you z is stuck between 2 constants? I'll just use c and d. So this would be like a rectangle in cylindrical, okay? So because we're in cylindrical, we have three variables, right? Theta, R, and Z. So if we restrict those variables between constants, what picture would that give you? Does anyone have an idea of what you'd be looking at?
Like a very tall washer.
Okay, so like a washer, okay. Let me try and draw that. Like, here's what a washer would look like.
I can't think of like what a washer that would be larger than a normal, yeah, like that.
Something like this, right? Okay, good. So I agree. This right here, you can see that the Z values, right? The Z's are stuck. The Z's are stuck between two constants. Also, we have an inner radius and an outer radius. That would be our, you know, I shouldn't have used R and S, sorry. Let me use something else. Let me use S and T. So we have an inner radius of S and an outer radius of T. And then in this case, what's our theta stuck between in this particular picture?
2 pi.
0 to 2 pi, right? But it doesn't have to be 0 to 2 pi, does it? It could be something else. So you could imagine that maybe it would be like a slice. Ooh, this was supposed to change. Maybe like a slice of this. Something like this. Do y'all see that little slice there? That slice is what I want to draw that again. It's kind of a different perspective. Let me see. Yeah, I guess that'll work. So this right here, the problem that I don't like about this is it looks like, come on, man. Okay. The problem that I didn't like is this looks like it's angled. That's straight over like that. So that's what a rectangular solid looks like in cylindrical coordinates, as opposed to the standard Cartesian rectangle, which would look like this, right? Okay, now that was just an exercise to get us to think about what things would look like. You know, where are we headed with this? Well, we want to be able to do triple integrals again, where our solid is best suited for this system. Now, just a little side note, when I was in college, my professor, actually, when I took calculus, I took 4 calculus courses. I took Cal 1, 2, 3, and 4, but they were each 3-hour courses instead of 4-hour courses. So instead of, like we do at standard Cal 1, 2, and 3, they're each 4 hours. I did Cal 1, 2, 3, and 4, and they're each 3 hours. So when I took Cal 4, it was basically all vector calculus. And my professor, he called the cylindrical coordinate system, he called it Planet Schlitz. And I guess Schlitz is a type of beer, like Schlitz beer. I don't know, is it a beer? And because cylindrical coordinates looks like a beer can, basically, right? So he called this Planet Schlitz. So when we're in cylindrical, we're on Planet Schlitz. That's what we're working in. Okay, so how do triple integrals work here? Well, if our region that we're integrating over, so you have to remember, this is all under the assumption that we have some triple integral over some solid E. Here we have some function of x, y, z, dv, right? This is what we started this chapter with, or this idea of triple integrals all started with this. If this E region that we're looking at is written in cylindrical coordinates, then we have that our theta can be stuck between two constants. Our r can be stuck between two functions of theta. And then the top and bottom of this solid are stuck between two functions of x. Now, notice that we're calling it u1 of r cosine theta, r sin theta. R cosine theta is really x, and r sine theta is y. So this is some surface that's a function of x and y. This is an upper surface that's also a function of x and y. And so this picture kind of shows you what a solid E in cylindrical coordinates could look like. So do y'all see the shadow on the ground? You'll see the shadow on the ground. That shadow on the ground is a polar region in two-dimensional space, right? It's like, it's so perfect for polar because Our thetas are between two constants. And then our radius, actually in this problem, is stuck between two functions of theta. But in this problem, it looks like those are constants. And then our surface is stuck, right? It's got like an upper surface, or solid has like an upper surface and then a lower surface on the bottom. Okay, so if we're going to do this, right, if this is what our solid E looks like, oops, if that's what our solid E looks like, then how does the triple integral change? Like, how do we convert this over? What does this become? What does this become, right? That's the question. And it's going to do what I think you'd naturally expect it to do. We're going to have our triple integral. Our first outer integral is going to go between alpha and beta, and we will go in with respect to theta on the outside integral. Then the middle integral will be our function of theta. That's the thing that's controlling the radius of the region, the polar region on the ground. That'll be with respect to r. And those two together, right? Those two together are basically polar, right? That's what polar was in two-dimensional space. So we will have to insert the r just like we did when we did polar to begin with. Now, as far as z, the inside, these are our two functions of x and y, but they've been converted over to polar, right? Really cylindrical, but polar. So we replace the x and y with r cosine theta and sine theta respectively. And then the function itself also has to be replaced. All the x, y's, and z's have to be replaced. X gets r cosine theta, y gets r sine theta, and z gets what? So we know what to switch x and y to. What do we switch z to? Nothing. Z stays z, okay? And that's why your inner integral will be with respect to z. Okay, so let's do one. And then once we do one, I think you'll see how this all comes together, hopefully. All right, so I'll have all this information up on the projection here whenever we do the problem. So here's the problem. I've already got this ready to go on another page. So let me bring that up. Okay, here we go. So find the triple integral over E of x dx with respect to volume if E is the region bounded by z equals 0. So z equals 0 is the ground. Z equals x plus y plus 5. That's a plane, right? So we've got the ground, and then we've got some plane. And then we have a cylinder of radius 2. Now notice this cylinder is missing the z, right? So this is basically a circle of radius 2 that extends up and down through the z-axis. And then we have another cylinder that's missing the z. So it also extends up and down the z-axis, but this one has a radius of 3 instead of 2. Right? So we are going to try and do this triple integral over this solid, and the solid is bounded by all of these. So let's try and get our heads around what this looks like. And I think that this is kind of where things get a little hard. I'll try and draw it over here. Let's start with, I have this cylinder here. Let's say that's this one, right? I have another cylinder that's a little bit bigger. Now remember, these cylinders just keep going up and down forever. I'm just trying to get an idea what they look like. So that's this one. I've got a plane, right? Now that plane, is it flat? Is that plane flat or straight up or horizontal? How do we know that this is not a flat plane? Not flat meaning all planes are flat, but I'm saying that that plane is not like parallel to the XY plane or to the XZ plane or to the ZX plane. How do we know that?
It doesn't equal.
What doesn't equal what?
It doesn't equal 0.
Well, if I moved everything to one side, it would equal 0, wouldn't it? Well, let me ask you this. How do you know this is a plane? Let me try it. Let me write it this way. This is a plane equation because we have 3 variables, x, y, and z, and they're all linear, right? That's what makes it a plane. The reason I know it's not flat is because the numbers in front give me my normal vector. And my normal vector has to be 1, 1, 1. And if you think about that, that normal vector, what would the normal vector be if my plane was flat, like parallel to the xy plane? What would my normal vector have to be?
0, 0, 1.
0, 0, 1 or 0, 0, 2 or 0, 0, 3 or 0, 0, -5. It would have to have 0 as the x component, 0 as the y component, right? And the z component would just have to be not 0. And then that would be a vector pointing up. If I was sideways like this, then I'd have 0 for the x and 0 for the z, but my y, I would have a y component sticking out. Does that make sense? Like you would have to have two, in order for your plane to be flat or straight up or turn that way, then you would have to have at least two of the variables be 0, or two of the components of the normal vector be 0. So I know that this is not flat, okay? So when I draw this plane, just going to go like this, okay? And then I have the ground. Okay, so the ground is going to be hard to draw, but here's the ground down here. Okay, so that's kind of stopping these cylinders. So we are trying to find the region that is enclosed or bounded by all of those. So let me see. I'm going to try and draw it. Do you all agree it would look like this? Something like this. Basically, right, this goes down like that to the ground. Do y'all see that? The two cylinders on the outsides creating the outsides of this solid. The ground is the bottom and the top is the plane. Any questions on that? Now, of course, I can have the computer do this for me, and the computer will do a much better job than I can. Let me clear that out. So here's the plane and the two cylinders and the ground. There it all is. Let me show you the solid, and I'll bring I'll just get all the surfaces out of there. There it is. Okay. So remember, this is the solid we're integrating over. When we look at this, could we do this the way we were doing it last time with Cartesian? So look at the domain, look at the shadow of this solid on the ground, right? The shadow of this solid on the ground is kind of that picture, which looks like, you know, we have an inner radius that was, I think, 2, and we have an outer radius here of this next one. That's 3. Could we do that? Could we do this region that's on the ground here? Could we do that using Cartesian? I mean, when you look at this, are your x's between two constants and then the y's between two functions of x? Or are the y's between two constants and your x between two functions of y? You don't understand what I'm saying? What do y'all think?
If you could, it'd be quite difficult.
Yeah, we could do it, but it would be hard because we'd probably have to break it up into multiple like regions, because you know, circles aren't functions of x, they're not functions of y. Then we'd have to solve for x or y, so we'd have square roots involved. But this is why we studied polar, because this is just a perfect polar region, right? So I know from this that, I'm going to go back to my other program here. I know from this that I'm looking at my E looks like this. I know that the shadow of this on the ground on the XY plane is going to be this thing. Man, my drawing sucks today. Okay, it's this region in here. And for that, I know that theta here is bounded between 0 and 2 pi. And my radius is just stuck between 2 and 3. Right? Now that gives me the bounds down here. How about my bound on top and my bound on the bottom here? Let's give me that.
The plane equations?
Plane equations. Okay, so the bottom one is the z equals 0, right? And the top one is z equals x plus y plus 5. So my z, my up and down here is bounded between those two things. And because we're in cylindrical coordinates, there is no conversion for z. Like z doesn't change to anything. Z stays z. So that's why I'm not, you know, x and y disappear and become something in terms of r and theta, but the z just stays z. And so this plane equation, x plus y plus 5, also stays. However, we no longer have x and y, right? We can't talk about x and y anymore. So we replace x with r cosine theta. We replace y with r sine theta. And then we have plus 5. So that's just the conversion of the xy using the polar conversion we made. Any questions? That's pretty much it. I mean, we've got everything we need to set up the integral. We're just now going to write this integral down and just make these substitutions. We're wanting the triple integral over e of x dv, but from our conversion into cylindrical, we're going to have triple integral here. My outer integral is going to go from 0 to 2 pi, and that'll be d theta. Then I move to the middle one. This will be going from 2 to 3, and that's going to be my dr. And now this is where I remember that because we did polar, I'm going to have an r in here, right? So I'm just going to slap this r in here right now. R is going to be in the integrand. But we still have this other inner integral that goes from 0 to, yes, r cosine theta plus r sine theta. I realize that that's an ugly limit of integration, but that is what the upper limit of integration is here, right? What do I still need? This is going to be dz, right? That's the inner one, but what am I missing in here? What are we integrating? X, right? That's what we're integrating. So I need that x in here. See, the r is just because we went to polar. Now I keep on saying we went to polar. Does everyone understand we really went to cylindrical, but cylindrical is really just polar? Yes, me.
Yeah.
Okay. So we need to replace this x. What are we going to replace the x in the integrand with?
Probably r cosine theta.
Sine theta, right? R cosine theta. And that's because we are now in cylindrical and x's and y's get converted, and this is our new integral. So this is it. This is the final version of the integral. The rest would be us just integrating this. I'm going to do just the first step of the integration, just to make sure you understand how to handle this, and then I'm going to stop. Okay, so the first integration, which means this first inner integral, when we do this, it is with respect to z, right? So that means we're going to be integrating r squared cosine theta with respect to z, meaning we have to treat r and theta like constants. So the antiderivative of that will just be itself, right, times z. And then evaluating that at z equals 0 to z equals, yes, this ugly thing, r cosine theta plus r sine theta plus 5. That's just the inner integral. Then we go dr d theta. So nice thing, when we plug in 0, we get 0 here, it's gone. But when we plug this in, every single one of these terms, these 3 terms, gets hit with an r squared cosine theta. So I'm going to write that out, but I think that's where I'm going to stop. Are there any questions? Okay, so here we go. We've got this piece gets hit with that, so we'll have r cubed cosine squared theta. Then we have plus r cubed and then cosine theta sine theta. And then we have plus 5r squared cosine theta. All of that dr d theta. This would be pretty easy to integrate. with respect to R, right? Because you treat all this cosine sine stuff as constant. So these are just going to be power rules on those. And what'll be even nicer is that you're just going to be plugging numbers in for those R's. So when you get through the middle integration here, you're just going to have an answer that has, you know, just trig functions, sine and cosine, and you should be able to handle those with your Cal 2 stuff. Some of them are easy, like, well, cosine squared, you'd wind up with a power reducing formula. Cosine sine, you could just, that's just a basic U sub, and cosine by itself, that's not even worth talking about, but it's all doable. So I'm going to stop there if that's okay with everyone, just to save time. And I'll show you, if you did work through that at the end of it all, your answer would come out to be 65 pi over 4. Okay, so I just had the computer do the whole thing for me. Any questions?
So this is like the polar version, or the polar version for triple integrals.
Polar version for three-dimensional space, exactly.
Okay.
Yep.
And then next we're going to do spherical.
Yep.
Right. Okay.
Yep. Yeah, and spherical is a complete change. Like everything changes in spherical. The way we view it, the way we do things is vastly different than here. Because here, X gets the change that we did in polar, Y gets the change that we did in polar, and Z stays the same. In spherical, all three change, and none of them are like, we don't keep the polar idea with us at all. We throw the polar idea away completely. Okay. All right, let's do another example. So this one says, so I guess the question for you becomes, at some point when you're presented with a triple integral, which, are you going to use Cartesian or are you going to use cylindrical, right? And what dictates that is the region itself. Like if the region is better off doing Cartesian, then you want to use Cartesian, right? Like on the problem I gave y'all for, I gave y'all that problem for the mini exam where you had to find like the volume above a tetrahedron and below a paraboloid. The region, the shadow on the ground, I believe, was a triangle. Yes. And so if you have a triangle on the ground, well, then you probably want to stick with Cartesian, right? Because it'd be hard to describe a triangle on the ground using polar coordinates. However, on the problem where you had to drill out that thing from the sphere, that's polar because your region on the ground is a good polar region. So that's what dictates what you're going to use. So when you look at a problem like this, it says find the volume of the solid between the cylinders, x squared plus y squared equals 4, x squared plus y squared equals 16, which also lies within this sphere. You're going to have to kind of draw the picture first, then that will determine whether or not you're going to use Cartesian, cylindrical, or spherical. We don't even have spherical yet, but so you need to see what the region looks like. You need to see what the domain on the XY plane looks like. So let's do this one. There's something different about this problem. Is this even asking you for a triple integral? It just says find the volume, right? Can we use triple integrals to find volumes of three-dimensional solids? Yeah, right, Margie? The triple integral over some solid E of 1 dV is equal to the volume of E. That was from last class. I put that up there for everyone. Just like we learned before that the double integral over D of 1 dA is equal to the area of D. Now that we're in triple integral, the triple integral of the constant 1 function with respect to volume over this region E should give us its volume. And just by the way, if we were to keep going with this and have a quadruple integral over something, I'm going to just call it, let's say, capital G of 1 D, well, we don't even know what we call this. I'm going to call it V tilde because it's not really even volume anymore. This would give us, what do we call it, right? Like it's something to do with G, right? It's volume, but you couldn't really call it a volume because it's 4-dimensional. So we could call this, like, a lot of times we call it a hypervolume. like we could get a numerical answer. It's just like, what does it mean physically? That's a deeper question. But I'm just saying this extends out. You can just keep doing this. This whole one, the idea of one here, and then whatever it is, double integral, triple, quadruple, or even back to single integral, right? That right there, that just gives you the length of the interval that you're integrating over. So if this goes from A to B, this gives you the length of that interval. Here, if you're integrating 1 over D, this gives you the area. Here's the volume, here's the hypervolume, and so on and so forth. Okay, I am going off track here. Okay, here we go. Now, I'm going to use this formula, right? But I need to get a grasp on what E looks like. So again, I've got 2 cylinders opening up the Z-axis. One has a radius of 2. The other has a radius of 4 this time. But these things keep going forever. But I'm trying to find the volume of the solid that's bounded by these, but also inside of this sphere of radius 6, right? This is a sphere of radius 6. X squared plus y squared plus z squared is 36. Okay, so maybe I'm going to draw this again. I don't like that picture. I'm going to draw my sphere first. This is a sphere that has a radius of 6. And then I've got this cylinder that I know is going to punch through here that has a radius of 4. And then I have another cylinder inside of that punches through there. It has a radius of 2. So can you see the solid we're talking about? It's the one that's bounded by all of those. Again, it's hard to draw. It's hard to draw. I mean, so let's look at what it's not first. It's not this. Why is it not just this? What's wrong with my picture?
Missing
The curve on the top.
so the sphere on top.
Yeah, it shouldn't be flat on the top and the bottom because the sphere is what's capping it off on the top and bottom, right? So there should actually be more of a curve onto this thing. So on the top, it should be like this. Oh, wow, that's terrible. Don't like that at all. There we go. Something like that. It's a little better. And on the bottom, we have the same thing. We have some sort of curve to it. So I think you would admit that that's kind of an odd shape, right? That's not something that you can just go to a textbook and look up the volume formula for it, right? This is something that we could figure out, but it's not something well known. Again, the computer can do a much better job of this. I thought I had it. There it is. So here's our sphere, here are 2 cylinders, and now let me just pull all the graphs out, and there is the solid that we're trying to find the volume of. Okay. So if we look at it from the top, and we look at the ground, right? The ground is perfect, again, for a polar region. So that's where I'm going to go with this. I'm going to look at the XY plane. I've got an inner circle here of radius 2, and then an outer circle of radius 4. In terms of polar, that's pretty simple. That's just between 0 and 2 pi again. And then my radius is just between 2 and 4. The big question is, what's the restriction on Z? What do y'all think? What's gonna be dictating the top of this thing and the bottom?
The equation of the sphere.
The equation of the sphere, right? Solved for what variable?
For Z.
For Z, right? We've got to solve it for Z. Now, when we solve it for Z, we're going to get a plus or minus, aren't we? Because we're going to take a square root. The positive would be the top, and the negative would be the bottom. Do y'all agree with that? So let me solve this for Z. If I solve that for Z, I'm going to just do it. It'll be plus or minus the square root of 36 minus x squared minus y squared. So we bring the x squared and y squared to the other side. We take the square root, plus or minus. So that should be my restriction, right? Z should be between those two surfaces. Now, do we want to do that, or do we want to use the symmetry of the problem? Meaning we could just cut this in half, right? Find the volume of that top half and just double the answer. I like that idea because it forces me to only work with one of the square roots instead of both. So that's what I'm doing. I'm just going to remember that what we're going to do is we're going to double our answer at the end. So here on Z, my restriction is between 0 and the square root of 36 minus x squared minus y squared. Any questions?
Are we going to turn that into polar?
Yeah, so at this point, you look at this, you're like, okay, Z is restricted between 0 and this, but this has x's and y's in it still. Can't have x's and y's. So we need to convert those. And hopefully you just remember that that's really 36 minus, take the negative out. And x squared plus y squared is r squared when you go to polar. So this really just turns into Z is bounded between 0 and the square root of 36 minus r squared. Much better to work with there. And I think we're ready. So here we go. It's the triple integral. I'm going to do twice the triple integral. The 2's because I'm only doing the top half in the integral. 0 to 2 pi, 2 to 4, 0 to the square root of 16 minus r squared. Okay, who wants to tell me what goes in the integrand? What goes in here?
36 is what, not 16.
Oh, 36. I don't know why I did 16. Thank you. 36 minus r squared. So what goes in here?
1 times r.
So we're using the formula that the integrand should be a 1, right? But we have to have an r in there because we went to cylindrical / polar. So even though there's a 1 there, we have to put the r there, then dz, then dr, then d theta. So I will highlight again that there's really a 1 there, right? There's a 1, but it's r because we went to polar. I always say polar. I mean, I don't know why. I've always just liked to just say polar. And that's it. We evaluate that. So we integrate that with respect to Z first. What would the antiderivative of this with respect to Z be?
RZ.
RZ evaluate at the 2 endpoints. That'll be nice. When you plug in this, you'll have a basic U substitution. And then from there on, it's just constants and everything should work out nice. So I'm going to just show you again what the answer would be if you were to work through this. Now, when I put it in the computer, notice the way I put it in, 0 to 2 pi, 2 to 4, and I did not choose to double the integral and go from 0 to square root of 36 minus r squared. I just went from negative root 36 minus r squared to positive, and then did the 1r and then dz, dr, d theta, and then went through all this. It's actually a really ugly answer. It's like the exact version of the answer is really ugly. So I just got a decimal answer. It's about 383.595 cubic, whatever, cubic feet, cubic inches, cubic, miles, whatever. Okay, that's it. There's only 3 problems for homework out of here. All right. It's really just for you to understand that this is available to us. And now we are going to go and look at spherical. All right, so for spherical coordinates, we are going to change our whole approach on everything. Remember, at this point, let me clear this out. At this point, we have 2 ways to talk about a point in 3-dimensional space. Okay, the 2 ways we have right now. So if I want to get to some point, I can go, let me do it this way. I can go out x, right? I can go out some x, out some y, and then up some z, and I'll be somewhere, and we call that the point x, y, z, and that is Cartesian, okay? We could have another way of looking at that would be instead of me saying go out X, Y, Z, I could say start at the origin, and here's X, here's Y. And imagine that you're looking down the X axis, and then I'm going to tell you to rotate by some angle. So you rotate by some angle theta. Okay, so you rotate by some angle theta. Then you walk out some distance R. And then I give you the Z value, which tells you, I don't know, move up a certain amount Z, and that'll give you some point here. And that's cylindrical. Okay. For both of these scenarios, in order to get to the point, you need three things, right? You either need to know X, Y, Z, that'll get you to the point in Cartesian, or you need to know theta, R, and Z, that'll get you there in cylindrical. This new system, spherical, works the same way. We need three things to get to the point, but it's the way we get there that's weird, okay? So let me try and explain it first visually like this, and then I'll show you the nice animations. So the way spherical works is we've got our X, Y, Z, okay, our standard Cartesian. And now what we're gonna do is we're gonna stand at the origin, okay? And this is kind of really hard to explain. So imagine that this is you, okay? There's you standing there at the origin, all right? You're standing at the origin and you're looking down the x-axis, okay? Like, so imagine you turn your body so that you're facing down the x-axis, right? Okay, and that right there is 0 for an angle. But I want you to put your head looking straight up the z-axis. So your eyeballs are actually looking straight up the z-axis, but your shoulders are kind of squared up, so your body's facing down the x-axis. Understand? We understand that kind of? I'm going to give you two angles. Okay? I'm going to give you two angles. The first one, theta, is going to be like it was in polar. It's going to be this right here. It's going to be the angle I want you to turn your shoulders. Okay? So down the x-axis is 0. If you turn your shoulders a little bit, like 10 degrees, you'll be turning, you know, what, kind of counterclockwise if you're looking from the top. Okay, so that's your theta. Now, remember, your eyes are still up though, right? Your eyes are still up, so you turn your shoulders. Now I give you a second angle. Now this is theta. The second angle is phi or phi. I've heard it. Have y'all heard that Greek letter before? Phi or phi. Okay, so people pronounce it different ways. Like if it's like a Greek fraternity or something, it's like sigma phi epsilon, but then you'll hear other people in physics call it phi. So I think it's debatable how you want to pronounce it. I just like do it both ways. I'll say phi or phi, okay? So that angle is the angle you want to rotate your head. Remember, you're looking straight up, right? You're going to rotate down from looking straight up by that phi or phi, okay? So you're standing there, you're looking down the x-axis, or you're facing down the x-axis, you're looking straight up, and now I'm going to tell you rotate by theta, you turn, and I give you phi or phi, and you start coming down, okay? And then I'm going to tell you how far to walk out from that. So that distance that I tell you to walk out, I'm not going to call it R, we're going to call it rho. So you walk out a certain distance, and we're going to call that rho. And you'll be at a point, won't you? You'll be somewhere. You'll be somewhere in three-dimensional space. That's spherical. Now let me show it to you with a computer instead of me drawing it, because the computer, I'm going to be able to, I think, animate it a little better. Make this a little larger for you. Okay, so here, this is our x-axis. So theta is the angle we're going to be swinging kind of our shoulders, kind of rotating around the z-axis. And so there's theta, I'm going to fix it there. The phi, remember, this is 0 for phi. So 0 for phi is straight up. If I start saying, you know, move down or give phi an angle, like let's say pi over 4 or 45 degrees, you're going to be aimed like this. There's 45 degrees. And then rho is the actual distance you walk out. So do you all agree that I could get to any point in three-dimensional space if someone gives me theta, phi, and rho? Right? Okay, so that's spherical coordinates. Now, there are some restrictions that we have to think about here. Theta really should always stay between 0 and 2 pi, because that'll give you one full revolution, right? The phi has a restriction too. It should only go between 0 and pi, because remember, phi is straight up is 0, right? Straight up is 0. So straight down would be a rotation of 180 degrees, and that's going to be pi. Anything past that would take you the other direction, upside down. Does that make sense? You'd come around the bottom and come back up. But if you wanted to be on that other side, you would just swing theta around instead. So if I wanted to be at a point over here, let's say where my cursor is, I wouldn't want to swing phi down and come around. Instead, I would just take theta and swing theta around so that I'm over there in that octant. I hope that makes sense. Any questions on it? Can you visualize what it would look like geometrically if your theta was between two constants, let's say alpha and beta, and let's say that your phi was between two others. I'm just going to call it P1 and P2 for phi 1 and phi 2. And let's say your rho is stuck between two different radius values, R1 and R2. Can you visualize what that would look like? Because this is a rectangle in spherical coordinates. Can you visualize a rectangle in spherical coordinates? I mean, it's hard to describe. Can someone try? I don't know.
Kind of like a shell.
Like a what?
Like a shell of the sphere.
Like a shell of the sphere. Okay. I like to think of it like this. Imagine that you had a coconut. Okay, you know how a coconut has an outside and it has an inside? Imagine that you were standing there, at the origin, and you're inside the coconut, and you have this like laser where you shoot the laser and it's going to cut the coconut. And all you're allowed to do is move up and down with your laser and left and right with your laser. And so you just go up, over, down, over, and cut out like a square. And it would look like this. I have a picture for you. This is basically it right here. You'll see that? So if we adjust, the radius, the outer radius, it just makes our coconut bigger. The inner surface and outer surface. My theta adjusts, whatever my theta is between will adjust how much I'm swinging left and right. And then the phi restrictions will determine how much I'm going kind of from the z-axis straight up to down. Whoa. So do you all agree that these spherical rectangles are really strange looking shapes? I mean, not strange and not like you could never imagine them, but it's definitely different than a box, right? I mean, it's definitely not a box. And it's also not a it's not a cylindrical rectangle. So why is it that you think that we are so interested in spherical coordinates? Why do you think that we like to work in spherical coordinates? Sorry, I'm eating. Why do you think spherical coordinates were something that our minds figured we should try and approach things this way?
And it kind of feels like with everything else in Cal 3, it's just kind of a consequential next step in how polar works.
Probably because of the shape of the Earth.
Yeah, we live on a sphere, right? We live on a sphere. So look, if I were to just take all these, let me just make a sphere here. There we go, right? So that's basically me letting theta go from 0 to 2 pi. That's me letting phi go from 0 to pi. And that's letting the radius, well, I might have a coconut here still if you could see the inside. But what's interesting about this shape is that, let's say you wanted to move from, let's say, the top of that down to the bottom, like so, from the North Pole to the South Pole, right? That's only changing one constant, right? The only thing that changes in that is phi. Theta stays the same, and the rho stays the same. Whereas if you tried to move along a sphere like that in Cartesian, everything's changing, right? The x, the y, and the z are all varying as you move along that. But in spherical coordinates, it's much easier to move that way. Also, if you go across, you know, like this, there, you fix your rho and you fix your phi, and you just let your theta change, and you can go around the sphere. So it's because we live on a sphere and that many things in the universe are spherical, that it's useful to have a coordinate system that's easy to work with for spheres. If we lived on a cylinder, right, if the Earth was shaped like a beer can, then we would probably be really partial to doing cylindrical coordinates, because that would be what we physically lived on. All right, so now we know that when you go from Cartesian to cylindrical, we have to use the polar conversions. What do we do to convert from Cartesian to spherical? And that is not a simple thing, okay? I actually skipped over it already. Here it is. It's this right here, Cartesians. So if you want to go from Cartesian to spherical, what you have to do is replace x. Okay, there's a lot going on here. You have to replace x with not r cosine theta like it was in polar. It gets replaced with rho cosine theta sine phi. Then you replace y with rho sine phi, sine theta sine phi. And then you replace z with rho cosine phi. Those are the three conversions that you have to make. Your theta will always be between 0 and 2 pi, and your phi will be between 0 and pi, and your rho will always be a positive number or 0. And we have, do you remember how we had that nice relationship back in polar, that x squared plus y squared was r squared? Well, in spherical coordinates, x squared plus y squared plus z squared is rho squared. That's something we're going to need to know. And that's it. Those are your conversions. And from that, we move on to the triple integral. We'll have to reference it, so I will bring that back up later, because usually students don't memorize this right away. You can kind of memorize it. I don't know, maybe. Do y'all see that? Do y'all see that rho cosine theta, rho sine theta is kind of like r cosine theta, r sine theta, like from polar? It's kind of the same. R cosine theta, r sine theta. The thing is, what you're adding to both of those are the sine phi or sine phi. So both of those get a sine phi. So think it's polar, but I have to add sine phi into it. And then the z is new. Z has to be rho cosine phi. Okay. All right. So how does the triple integral work? Well, if your theta is between two constants, your phi is between two constants, and your rho is between two constants. This is a rectangle, right? This is a rectangle in spherical. If that's the case, then your triple integral becomes, and when I say your triple integral, I'm talking about that standard triple integral from Cartesian, where we say, what does that turn into? What does that turn into? Well, the good news is that to do the f of x, y, z, you're just going to take your f and replace x, y, and z with what the spherical conversions are, right? These are the conversions I just showed you. But do you see this in yellow? Rho squared sine phi? That has to be included. Just like when we did polar, you had to have an r squared. When you do spherical conversions, you're going to have a rho squared sine phi. Now, I can't explain to you right this second what that's from, but I will in the next section show you where this comes from, if we have time. And then you'll have d rho d theta, d rho d phi d theta, okay? What else? I think that's it. Give me just a second, if you don't mind. Someone's at my door and my dogs are going crazy. I don't know if y'all can hear that. All right, sorry about that. I don't know what that was. All right, so notice that in this formula, we're only looking at integrating in spherical coordinates over a rectangular solid. So everything's stuck between constants. You could make this more complicated, where your theta is between two constants, your phi is between two functions of theta, and your rho is between two functions of theta and phi. But we're going to keep it simple. In this section, we're not going to go past this basic idea, okay? Which is good news, all right? All right, so here we go. Now, I've kind of given this away already because I'm showing you the picture here, but it says find the triple integral over e of e to the square root of x squared plus y squared plus z squared dv, where e is the region in the first octant between the spheres of radius 4 and 9. So we need to understand what this region looks like, right? So sphere of radius 4, sphere of radius 9, 4 and 9. And so we want the region that's in between those in the first octant, which looks like this. Okay. So that's kind of like a coconut, isn't it? I'm going to take a little picture of this, take it with us. I have a question. Here's the problem. Hopefully you could kind of visualize this with just what they gave you right here. So my question to you is this: could we do this with Cartesian?
Yes, but
Probably.
It'd be messy, but you can do it.
And we might be able to, but you have to be careful, because if we did Cartesian, we'd be looking at the ground, right? The XY plane, and we'd be trying to figure out what the region on the ground looks like. And that's a problem, because we actually have this, right? But that's not the region on the ground, because that's just this outer edge. And yes, there's a surface below it and a surface above it, but there's also this edge right here where you have a different surface on the bottom and a different surface on the top. So we would also have to take into account this region. And so we'd have two triple integrals that we would have to do, one over the blue part, one over the black part. Does that make sense? And in each one of those, we'd have a different surface on the bottom, different surface on the top. Well, they would all have the same top surface, but the bottom here on this part in the black, the z would be 0. On the bottom here, the z would be the equation of that sphere. Okay, so that looks maybe, okay, but more work than I think it's worth. How about in cylindrical? Could you do cylindrical? Same problem, right? I mean, you basically have the ground is this and this. And so, yeah, these are probably better for cylindrical, aren't they? Like these would be better for cylindrical because you could do the black and the blue in polar pretty easily. But again, it's the top and bottom surfaces aren't going to be nice. Like they aren't going to be the same. But if we can realize that this is a spherical region, just a spherical rectangle, the problem becomes very easy because here are, let's see if y'all can help me out. Do we have just restrictions on these three things? Are they easy to determine? So if we're in the first octant only, and my radius has to go between 4 and 9, oops, 9, then what's my restriction on theta? So that's my turning this way, right? So what would that be?
0 to pi over 2.
0 to pi over 2, because I'm only doing a quarter rotation. I'm not doing a full rotation. So here's a quarter rotation. That's basically this right here, 0 to pi over 2. Okay, what about phi?
0 to pi over 2.
Same thing, right? This is straight up as 0, and then we want to rotate down through to the bottom here, and that's our phi, and that's going to be stuck between 0 and pi over 2 also. And then the rho is just the inner radius to the outer radius, which should be our 4 to 9. And now we set up the triple integral. Okay, so we're going to be using this formula here. And remember that we have to convert x to this, y to this, z to this, and then we have this identity. So when we look at this triple integral over e of e to the square root of x squared plus y squared plus z squared dv, this now becomes triple integral over, well, we can do these limits of integration now. We can go 0 to pi over 2, 0 to pi over 2, and 4 to 9. And that should be d theta, d phi, and d rho. By the way, could I change the order of integration here, you think? If these are all constants, could I switch these up? Yeah,
Yes.
just like we did with traditional Cartesian. If they're all between constants, you can. All right, so that's this setup. This is converted over. Now e to the square root of what? Well, what's x squared plus y squared plus z squared?
Rho squared.
That's rho squared, right? So that's going to be the square root of rho squared. That's just going to give us rho. And I'm done? No, I'm not done, right? I still have to put in here rho squared sine phi. And that has to be there because anytime we go from Cartesian to spherical, we have to include that. So that becomes 0 to pi over 2, 0 to pi over 2, 4 to 9, e to the rho times rho squared, oops, rho squared sine phi, d rho, d phi, sorry, d theta. And then we could go after that integral now. We would integrate with respect to rho first. So you'd have to do e to the rho times rho squared. That would probably be integration by parts twice. And then after you get that, you're going to plug in numbers. So everything's going to be nice. And then you're going to have some trig function with phi in it. You can integrate that, two constants. This should be smooth sailing after that integration by parts. Now, remember, we just said that maybe you could have done this in Cartesian. Maybe you could have done it with cylindrical, maybe. I doubt you'd be able to do the integration, though. I think the integration would be too much. If you kept it in Cartesian or cylindrical, I'm not sure you'd be able to do that first integration step. But by doing the spherical conversion, it should be pretty good. Okay. I'm done with that. Y'all all right? Gonna move on to the next example. Oh, that was it. Okay. Three problems here. So when you're doing your homework, it's always easy because you know you're supposed to go to spherical, right? You're sitting there, you're looking at the problem, you're like, oh, somehow this is spherical. So you make your conversion. The problem again is when you're on a test and it's like, you know, how do I know I'm going to go spherical here? You have to have some understanding of the region for that to happen. No questions? All right, I had talked about skipping 12.8 and I thought about it more and I decided not to. So we are going to do 12.8. Change of variables. So let me just tell you a little bit about this section. If we just kind of back up and think about things, all this game that we've been playing in two-dimensional space, when we went from Cartesian to polar, all we're doing is changing our variables. So like in 2D, in two-dimensional space, when we went from Cartesian over to polar, we just made a decision to let x be equal to r cosine theta and y be equal to r sine theta. And then from that, you know, we had our polar conversion. And when we did our double integral and we converted it, we knew we had to get an r in there, dr d theta, right? This r kind of magically popped in here. We talked a little bit about where it came from, but all we did was change the variables. We went from x and y over to r and theta, right? That's what we did. It's a change of variables. In 3D, we actually just did two different changes of variables. One of them was Cartesian to cylindrical, and the other one was Cartesian to spherical. And in the first one, x went to r cosine theta, y went to r sine theta, z stayed z, right? But again, x and y changed to r and something with r and theta, and then the z stayed the same. But in the Cartesian to spherical, we just decided to replace x with rho cosine theta sine phi, and the rest, the other two, right? Sorry, the other two. It's just changing variables. That's it. That's all it is. We did it based on the geometry, right? We said, okay, we can, let's create this new thing, theta and phi and rho, and I tried to show you how you can visualize that. But there is nothing at all that is limiting us from changing any variable to any other thing we wanted to. Like we could do anything we want. I could just say, hey, look, everyone, let's go back to 2D. Let's go back to 2D, and I'm just going to make this conversion. Everywhere you see x, I want you to replace it with u squared sine of v. I don't know, I'm just making shit up right now, okay? And then y, I want you to replace it with v squared cosine of u plus v. That would be a change of variables. Everywhere you see x, it gets replaced with this. Everywhere you see y, it gets replaced with this, right? I changed the variables. Now, if I do a double integral, right? That dv, like over here, and I forgot to mention this, sorry. This right here, I mentioned it over here, that the r kind of like came from somewhere, right? And over here in the cylindrical, we had the r also appeared over here. And when we did the spherical, we had this, what was it? Rho squared sine phi, right, appears. And it's kind of like, where's that coming from, right? Like, why do we have to do that? Why is the r there? Why is this r here? So if I do a general change of variables just on a whim, I'm just going to create my own change of variables. There's something in here that we're going to have to put in here. And the question is, where is, like, how do I know what it is? And that's what this section is about. This section is about, if you were to change variables just arbitrarily, how do we account for that change of variables in this piece that must be included? Okay, so that's what it's about. With that, let me try and show you the way through the section. It's complicated. I don't want you to get hung up on things here because there's part of what I have to show you that we haven't even talked about yet. So you're just gonna have to kind of believe me, all right? But I'll do what I can. The main idea is that anytime you do a change of variables, and you can do that, you can change it to anything, that you will always have this piece here that is created that you have to be able to come up with on your own. Like you have to be able to generate what that is, like the R, and over here, the rho squared sine phi. All right, so change of variables. This is me just basically saying everything I just said, okay? You know, when we were sitting here with the Cartesian double integral, we let x be r cosine theta and y be r sine theta. What I'd like for you to do right now is instead of us using r and theta, let's use u and v instead. So instead of r, I want you to use u, and instead of theta, I want you to use v. And that would be the same. That would be the same conversion, wouldn't it? It would be a change of variables, just using two new dummy letters instead of r and theta. So more generally speaking, we have made a substitution where the x is replaced with some function of u and v, and the y is replaced with some new function of u and v. With that particular changing of variables in mind, I want us to look geometrically at what happens to a little patch of area when we make that conversion from Cartesian to polar, like visually what it looks like. So here it is. If we take a little rectangle in the Cartesian plane, so the one on the right is Cartesian. If we convert a little rectangle in Cartesian over to polar, then what we get is this new patch. That's the red, not the ignore these red vectors and the dotted lines, just this red patch over here, okay? So if we take this rectangle and convert it to polar, we get this weird shape. And the question is, what is the area of that shape? How is it related to the area of that shape? Are these two areas equal? Is this area twice as much as this one? Is it even like a scalar multiple? Maybe they're related by a function. Who knows? But there is something that relates the two. And if we go small enough, sorry, where is it? If we go small enough, okay, if we go to an infinitesimal, where we're talking about an infinitesimal rectangle over here, what happens is that, do you see that the error, the difference between the dotted red parallelogram and the red actual shape, do you see that that error goes to 0 if you take a limit, that they basically become the same shape, right? So if I can find a formula for the area of this parallelogram, that in the limit should be equivalent to the area of this red patch. So the next thing, and again, you're not going to be testing on this, it's just more of a visual connection that we're trying to make here. If I want to find the area of this, we know how to find the area of a parallelogram, don't we? If we're given two vectors. Okay, so that's what the next part's about. And again, I'm not going to go through all of this. The area of the red region is just the cross product of those two vectors that I showed you on the previous page. And then you can do properties of cross products and factor out this part. And then eventually at the end of this, again, I have to wave my hands because there's stuff we haven't talked about vector functions of more than one variable. That's chapter 13. And that's what they're using here. So this is one part I don't like about the textbook, because to prove something, they're using something that they haven't shown you. So if you can just trust that this right, where is it? If you can just trust that this right here gives you the area of that parallelogram, then we can move on. And what it is, well, I'm going to go to the next page because it hasn't blown up. This right here, the very important part right here, this right here is the part that, remember I was saying there's a question mark, like what does it become? Where did that R come from? Where did that rho squared sine phi come from? It's always going to be this right here. And we have a name for it. It's called the Jacobian or the Jacobian determinant. And so if we want to go from a double integral over some region D, where we have a function of x and y, and we want to convert that to two new variables, u and v, then we can convert our function here, or switch out our x, switch out our y, just like we did with r cosine theta, r sine theta. We will change our variables. So this is like the dr d theta, but we must include this piece. And that's actually where the r came from with the polar conversion. All right. So can you just for now, can you take that on faith and trust that? Yeah. Okay, if you can, then I'd like to prove to you why a polar conversion gives you R. All right, let's just see. So I'm going to work it out. I'm going to clear this and I'm going to copy it. So right now, my goal right now is to prove to you why it is that when we do a polar conversion, we have to throw an R in there. Okay, that's what I'm trying to prove to you. So first thing I'm going to do is I'm going to write down what the polar conversion is, the way that you're familiar with it. And then what I'm going to do is I'm going to say, okay, forget that for now. Instead, I'm going to do this. X is u cosine v, and y is u sine v. So in other words, I'm replacing r with u and theta with v, just so that it matches up with the formula I have up here. All right. Now, according to this formula, in order for us to figure out that part that we have to include, the Jacobian determinant, we need to take the partial of x with respect to u, multiply times the partial of y with respect to v, subtract the partial of x with respect to v times the partial of y with respect to u, and then make sure we take the absolute value of all of that. Okay, so let's take a look at this. Let's look at this first piece. What is the partial of x with respect to u? So look at this right here. What is the partial of that with respect to u? All right, so if we're doing that, we're treating cosine v like a constant. And so the derivative of that would be what?
It would be u cosine v squared over 2.
I think you're doing antiderivative.
Oh, I'm sorry.
No, it's all right. Just the derivative, right?
It would just be cosine v.
Cosine v, okay. All right, let's just get all of these. We need the next piece. That's partial of y with respect to v. Let's get that one. I'm just start listing all these out, and we'll put them all together. So that's one. We need the partial of y with respect to v. Okay, so we look at, here's y, partial of y with respect to v. We treat u like a constant. So what would be the partial of this? Someone else?
Cosine of v?
U cosine v,
Cosine.
right? U cosine v, because u is like a constant, it's gonna come for the ride. Okay, let's look at the next one. Partial of x with respect to v. So who wants to give me that? What's partial of this with respect to v?
Negative u sine v?
Negative u sine v. And then finally, the last one, partial of y with respect to u. So partial of this with respect to u, the u goes away, sine v stays, right? Okay, so let's find the Jacobian. I'm going to call it capital J. The Jacobian, and we'll take the absolute value of it, is going to be the partial of x with respect to u, which is cosine v, times partial of y with respect to v, which is this one, u cosine v, minus partial of x with respect to v, which is negative u sine v, and then times partial of y with respect to u, which is again sine v. And then, do y'all see what's going to happen here? U cosine squared v plus u sine squared v. We can factor out a u. And that's a 1, so we get absolute value of u. So this says that if we want to replace, if we want to make this change of variables, if we want to do it, then we better be willing to include this Jacobian in our integral. And so if I calculate the Jacobian, it's just u, but remember, what was u? U was r, right? So that's where the r comes from. And the reason I don't need the absolute value is because when we're talking about r in this conversion, the radius is always positive. So I don't need to consider a negative. So that's it. That's where it comes from. All right. Now, the next thing, we have 20 minutes left. Would you all like to see where rho squared sine phi comes from?
Yeah.
Yes? Okay, let's do it, because spherical is not easy. It's not as easy to show, okay? But I think it's worth it, all right? So I have to back up. I have to back up because I don't want to just give you the formula for it. I want, this is going to be a little exercise. I don't even know if we're going to be able to finish this now. I'm thinking about it. Okay, so yeah, this is the way I'll do it. Everyone just clear your minds for a second. Let's talk about determinants of matrices. Okay, so if you have a 2x2 matrix, A, B, C, D, I know some of you haven't taken this. If we want the determinant of that, what you do, and we've done this before, is you do A times D minus B times C. So you do multiply here and then subtract the diagonal here, right? That's a determinant of the matrix. Okay, now I just called this thing a Jacobian determinant, right? That's what I called it. Here's where it came from. You take the partial of x, sorry, partial of x with respect to u, partial of x with respect to the other variable v, then partial of y with respect to u, partial of y with respect to v. Okay, so notice the top row is just the x variable, and I'm taking the partials with respect to the two variables that I'm changing it to. So I'm going from x to u and v, right? So I do those partials, and then here's the other variable y with respect to u and v. If I ask you for the determinant of this matrix, you'll do this times this, which would be partial of x with respect to u times partial y with respect to v minus partial of u with respect to y. I got those backwards. Partial of y with respect to u, partial of x with respect to v, right? That would be the determinant of this. And that is actually the formula that I just showed you. Where is it? That's this right here. Okay. Understand? So if we're going to see, because if we're going to try and show the spherical conversion becomes rho squared sine phi, we have three variables, don't we? We have three variables. So if we're going to do this Jacobian determinant thing, we need to be able to do the determinant of a 3x3 matrix. So let's see if you know that. If this is A, B, C, D, E, F, G, H, I, does anyone know how to do the determinant of a 3x3? No, it's okay if you don't. I'll just show you. What you do is you take A first, okay, and you write it down, A. And you're going to multiply that by the determinant of this bottom corner. Okay, so now I need to take the determinant of E, F, H, I. Now what I do is I switch signs. Instead of doing A, I'm now going to do minus B. So now I'm doing B, right? So maybe I should have said this. When we did A, okay, when we did A, what I did is I circled A and then I ignored this down here and I got the determinant of these four. When I do the next piece, I switch signs, I go to B, I go negative B, and now I'm going to ignore this and do the determinant of these four here. Okay, so it'll become the determinant of DF, GI. And then I switch signs again. and I do plus, now I've moved on to C times, and now my determinant is going to be off of these four there. So determinant of D, E, G, H. You following me? Now, each of these is a determinant. So this would become A times E times I minus H times F minus B times D times I minus G times F plus C times D times H minus G times E. See how that works? So what if we had a 4x4? So now I'm starting to get crazy here. So to make things a little easier, I'm just going to call this X11, X12, X13, X21, X22, X. Oh wait, sorry, I'm doing a 4x4. X14, X21, 22, 23, X24, X31, X32, X33, X34, X41, X42, X43, X44. So
Are you really gonna do that?
what's that?
Are you really gonna do that?
I'm not gonna do the whole thing.
I was gonna say.
No, but I want to set
Hey,
up.
I'm taking linear algebra. I mean, I know how it's gonna go. Like
Exactly, right?
It gets really messy.
Oh yeah, it gets messy. It gets messy, definitely. But I'll do just the first step, okay? Because once you understand the pattern, you can do it for any size. So if we want to do this, what we'll do is what we did before. We'll start out with the first one here, okay? And then we're going to look at taking the determinant of everything else. So we'll have X11 and then times the determinant of X22, X23, X24, and then X32, X33, X34, X42, X43, X44. I didn't get a chance to state, the first number down here is what column I'm in. I'm sorry, what row I'm in. And the second number is what column I'm in. Okay, so the first row, first column, first row, second column, first row, third column, first row, fourth column, right? Okay, now next, what I'll do is I'll move to the next number, this right here. I'll ignore all this, and I'm going to do the determinant on that. And I change the sign, so it becomes minus X12. Now I have another 3x3 determinant. And then I'll switch to plus, and now I go to the next one, X13, then another 3x3. And then I go minus X14 and another 3x3. And we have to understand this 3x3 determinant is that. So we'd have to do all this work for just that one and that one and that one and that. It's a by hand computation that would suck, okay? But it could be done, yes. It could be done. All right. So if we're going to talk about a Jacobian determinant for a change of variables that goes from 3 variables to 3 variables, then our Jacobian determinant is going to be this. We have to do, let's see, our first variable is X, and we're going to change X over to 3 things. It's going to be, let's see, we'll have theta there. We have to change X over to phi, and X is also getting changed over to rho. Then I do Y also gets changed over to something with theta. Y gets changed over to something with phi. Y gets changed over to something with rho. And then Z gets changed over to something with theta. Z gets changed over to something with phi. And Z gets changed over to something with rho. And now I need the determinant of that. Okay. Now, I'm not going to write down what this determinant is right now. Okay, I'm not going to write it down. What I'm going to write down right now are what are our 3 conversions. So X got converted to rho cosine theta sine phi, right? Y got changed over to rho sine theta sine phi, right? And what did Z get changed over to?
Rho cosine theta. I'm sorry,
Phi.
phi.
Okay. Now look at these partial derivatives we need. We need 3 partial derivatives that are with respect to x. I'm sorry, 3 partial derivatives of x with respect to 3 different things. So let me start listing those out. The partial of x with respect to theta. Okay, so sine phi is a constant, rho is a constant. I'm just taking the derivative of that. That'll give me negative rho sine theta sine phi. With me? I also need the partial of x with respect to phi, which will be, okay, so this with respect to phi, I'm going to do rho, cosine theta doesn't change, and sine phi becomes cosine phi. Okay, I need the partial of x with respect to rho. Well, that's a nice one because if rho is my variable and these are constants, then that just becomes a 1, so it's just cosine theta sine phi. Okay, we've got 3 of the 9 partial derivatives. Moving on to y. I need all the partials with respect to the 3 variables. So partial y with respect to theta would be rho cosine theta sine phi. The partial of y with respect to phi would be, let's see, rho sine theta sine cosine of phi. And the partial of y with respect to rho would be just sine theta sine phi. You see that all I'm doing is just getting all the things here, and then I'm going to have to do the determinant. Okay, z. So partial of z with respect to theta is equal to what?
0.
Yay! That's the only one that was good. Okay, partial of z with respect to phi would be just negative rho sine phi. And then the partial of z with respect to rho would be just cosine phi. Isn't this fun? I'm going to see if I can write out the determinant real quick. This is going to
That
be,
0 will make things easier.
yeah, one of those zeros is
Slightly.
going to be nice, right?
Yeah.
So if I do the determinants, partial of x with respect to theta, so I'm doing this piece first, and then the times the determinant of this one, right? Determinant of these guys right here. I'm going to do that in my kind of mentally. It'll be partial of y, partial y with respect to phi, partial of z with respect to rho minus partial of z with respect to theta. Oh no, phi, sorry. Damn. See, it's so easy to make a mistake now. So I'm doing this times this, and then minus this times this. Partial y with respect to rho. Okay, I need you all to be checking my work here because if we mess one thing up, we're dead in the water. Okay. Is that okay? Moving on to the next piece. So now I'm going to do this piece here and be looking at that and that, those 2 here and those 2 here, ignoring that one. So I switch signs because that's part of the formula for the determinant. Partial x with respect to phi times, okay, now the determinant here to here, so partial y with respect to theta times partial z with respect to rho minus partial z with respect to theta, partial y with respect to rho. Okay, that takes care of that. Partial, just double checking here. I think I got it. Last one. This, and I'm doing the determinant on those two. So it'll be a plus partial x with respect to rho. And then we have partial y with respect to theta, partial z with respect to phi, minus partial z with respect to theta times partial y with respect to phi. All right. Now, if we compute this, we should get rho squared sine phi. All right, what's good here? Partial z with respect to theta is 0. Where is that? Anywhere? No. Where is it? Partial z right there. Is that the only place it appears?
No, it's also on the partial z. Respect to
So
zero.
this right here is gone, right? Because that's 0. And this one right here, because that's 0. That's about the only help we got, right? That's about the only help we got.
Well, if you had gone down row 1, like it might have been easier to do
If I would have
instead
done
of
what?
going across the. I mean, going down column 1, not instead of across row 1. You know what I mean?
Oh yeah, you mean doing your determinant a different way?
Yeah.
Yeah, I only did it that way. That's like the standard way that most people
Yeah.
see it. You know, I mean, there's other
But
ways.
usually when you do them, you target the zeros and go down those rows, or
Yeah,
go where you find the zeros.
yeah, go where you find the 0. I think it would make it easier. I still think we would still have a significant amount of simplification to do.
Yeah, it's not gonna be easy, but it'll be
Yeah.
slightly easier, like I said.
Slightly more efficient, right? I
Yeah.
think it would be. I just wanted to stick to the convention of what I've presented because this class is not about determinants,
Right. Yeah.
different ways to do determinants. I think they're already tricky enough,
Yeah.
especially once you get past 3 by 3. Okay, so I have 3 minutes. There's no way it's happening. So the idea now is that if I go in here and I replace, this right there and everywhere else I see that, right? And I just start plugging in all these things, I should get an expression where I should have a lot of like sine squared theta plus cosine squared thetas that turn into 1s, and sine squared phi's with cosine squared phi's that turn into 1s. And all of this, when you finish it, should turn out to be your rho squared sine phi. I'm going to leave that to you as an exercise to see if you can do it just for fun. I mean, because it should work, as long as we didn't make any mistakes, it should work out. And that would then show you where that comes from. And so now for any change of variables, you always have this ability to change it as long as you account for the Jacobian determinant. All right. I regret that I can't explain to you in more detail why it's that. I mean, if I go back and try and convince you that the area of the parallelogram, the thing that's hard for me to convince you of right now is this piece right here. Like, how do I explain to you that this vector is the change in u times this r vector sub u? That's actually the partial derivative of a vector function that draws this surface. And so we haven't talked about that. We know how to draw, we have learned vector functions, RT equals something. And those draw curves in 3-dimensional or 2-dimensional space. We have not studied in this class vector functions of more than one variable. We will, it's chapter 13. Those draw surfaces in 3-dimensional space. And so this is saying that this right here is the partial derivative of that surface function with respect to u. And it's just, I mean, if we haven't talked about it, we haven't talked about it, right? But what if you can agree with this, that this vector is this, and this vector is this, then the area of a parallelogram is just the magnitude of the cross product of those two vectors. That's from the very first chapter. Give me two vectors, take the magnitude of the cross product, gives me the area of the parallelogram. So that's what the next part of this little thing is okay, take the area will be approximately the cross product of those two vectors. And then it's just a matter of using some properties that, this is a constant, they can come out. And then you cross these two vectors. And when you cross these two vectors, here's the actual cross product right here. And when you cross them, you get this vector. And then you take the magnitude of that vector. And when you do that, you get this. Okay, so again, you have to, once you believe that that's true, which again, I can't tell you, I can't prove to you yet, then it's just computational stuff. All right. Okay, well, we're going to end it here. And when we come back next class, I'm going to do two examples of this, where we're going to make a change of variables, but they aren't going to be it's not going to be going from Cartesian to polar or Cartesian to spherical. It's just going to be Cartesian to something new. And you'll see the reason why we do it is because sometimes when we make our conversion, sometimes our region sucks. Sometimes the region we're integrating sucks. And if we make a change of variables, the region of integration gets nicer. And other times it's actually the integral itself that sucks. So I have this example here. This integral is not possible to do easily in Cartesian. Even though the region's not that bad, I can show you that region later. But if you were to try and integrate that by hand, you're not gonna be able to. In fact, I was hoping we'd get to this. I put it into Symbolab. Symbolab can't do it. I put it into Mathematica. Mathematica can't do it unless they bring in an error function, an exponential integral error function. So that can't be done by hand. But if we make a simple change of variables, just over to a new system, the integral becomes easy and we can do it. So next class, you'll see how this can be useful. And then after that, we're done with chapter 12. We start chapter 13, vector fields, vector spaces, flux and all that stuff, Green's theorem, Stokes theorem, divergence theorem. Everyone have a great day. Do those problems for 12, 6, and 7. Talk to you later.
Thank you, sir.